Hi there guys, welcome to another Chem Complete video, and we're going to focus on some Organic Chemistry 2 in this new lecture series, and that is the carboxylic acid derivatives. So carboxylic acids are a type of functional group that are mildly acidic in comparison to stronger acids like hydrochloric acid or sulfuric acid, things of that nature. Carboxylic acids have an entire set of derivatives that we tend to study towards the end of Organic Chemistry 2. And the primary derivatives are acid chlorides, sometimes referred to as acid halides, although chlorides tend to be the most common ones. We have anhydrides, we have esters, and then we also have amides. And those are the primary derivatives that come from carboxylic acids. So this is probably going to be a short introductory lecture. We're going to cover each of these subsequently as we go along in the series. So the first one's just going to give the reactivity series and talk about each one, and then we will have each individual lecture that breaks down, acid chlorides and anhydrides and so on and so forth. They'll each have their own respective lecture. So to get started here, if you take a look, we've got the normal carboxylic acid. Now, when we have a carboxylic acid, one of the things that we should consider, and this is basically in relation to the derivatives that we have here. When we're dealing with this, a carboxylic acid, which has this portionality right here, right? This is really what defines the carboxylic acid. You've got a partial negative group here that's hanging off of this carbonyl group. So the carbonyl is partially positive here, partially negative up here, and then we have some sort of a partially negative group. In the case of carboxylic acids, what we end up with is the OH group. So the derivatives are going to be groups that also contain electronegative groups in this position. Okay, so a lot of students, when I get to this point in lecture, they'll turn around and they'll ask, well, if you have all these others, the amide, the ester, the anhydride, how come ketones and aldehydes are in their own chapter? Well, that's a good question. If you take a look at, for instance, an aldehyde, we have C double bond O and then an H. An H is not particularly electronegative, right? That's not the case. In fact, an H is electropositive. And if we were to make this a ketone like a CH3, that would also be electropositive. It would not be electronegative. So it's important to keep that in mind. We're really dealing, the derivatives are going to deal with compounds that have this electronegative or polar functionality that's to the right of the carbonyl. You could say to the left by standard methodical procedure. I'm putting it on the right each time. But anytime you find these groups on one side of the carbonyl, you end up with an acid derivative. So what are they? We mentioned them before, and I sort of color-coded this if you take a look at it here. So we've got the acid chloride. The red is supposed to represent high reactivity when we're dealing with this. So you've got the acid chlorides are the most reactive derivatives that come from the carboxylic acid. Then you have the anhydrides. Those are relatively reactive. The esters, we're starting to lose some of the reactivity. And then the amides are the least reactive out of the bunch. So if you were to take a look at this here, the general procedure would be that we go down this way, and we can call this reactivity. Okay? Reactivity. So what this means is that the acid chloride is the most reactive derivative. So acid chlorides can be turned into anhydrides, into esters, and into amides, among other things which we will discuss in the acid chloride lecture. Then anhydrides can be turned into esters and amides, but they cannot be turned into acid chlorides directly. Esters can be turned into amides, but they can't be turned into anhydrides and acid chlorides. And then finally, the lowly amide cannot be turned into any of these guys that are up here. It is by itself down there. Now, something that is very important to note is that all of these, through one reaction or another, can be turned back into a carboxylic acid, and every carboxylic acid can be turned into an acid chloride, and then subsequently into all of these other potential compounds. So you can sort of reset the chain. Let's say that I have an amide, and I would like to turn that amide into an acid chloride. Well, while I can't do that with a direct reaction, I can take the amide back up to a carboxylic acid and then start that back over into an acid chloride. Okay? Now, the next thing I want to do is I want to discuss the reason for the reactivity that we see. So why are acid chlorides more reactive than amides, so on and so forth. So let's take a look at the reasoning behind that reactivity. So the reactivity is going to come from the group, the electronegative group we were talking about, that is directly attached to the carbonyl. So if we take a look, we've got a chlorine here. Hang on, let me select the correct tool. We've got a chlorine here. That's a little too big. So let's move that back down. Okay. Let's try this. There you go. Okay, we got a chlorine here. We have basically another carboxylic group here. It's a carboxylate anion. We have a alkoxide here, so an OCH3, and then we have an amine here. So the key for this in terms of the reactivity is going to be that these groups that I've highlighted here in the rose, or the pink, are going to need to leave. They're going to be leaving groups. So something will attack the carbonyl and it will kick off this group. Well, we know that chlorines are very good leaving groups in terms of their reactivity. They tend to go into solution as good leaving groups. They're weak bases, so they tend not to interfere with other reactions. Right here we have a nice leaving group because this leaving group is going to be resonance stabilized. So anytime we have resonance, we have the ability to delocalize these charges over more than one spot. And so the ability to move that charge between these two oxygens is crucial here, making the anhydride a pretty good leaving group. And then we get into the alkoxide, which is the OCH3- or whatever OR group you might have for your ester. This is starting to get a bit stronger. Okay, so these guys up here, these would be considered weak as far as the base goes. So remember that weak bases make good leaving groups. That's the sort of the conjugate analogy that we draw there when we were back in Organic 1. When we talk about an alkoxide, that's a pretty strong base. Okay, so we're getting stronger here. We have to be careful. That's why the ester is not as reactive as the other two are. And then finally, when we come down to an amide, to have an amide anion, an NH2 like this is a very strong base, very, very strong. And so when we get to a point like this, that helps to show why the amide is so non-reactive or unreactive in comparison to the other derivatives, because it's very difficult to kick off an NH2 and get it to stay off. Okay, this is going to be a very poor leaving group because it's a very strong base. So the better the leaving group, the higher the reactivity on the chart, right? So here's reactivity. The acid chlorides reign supreme in terms of their reactivity because chlorine is such a good leaving group. Then the anhydrides, we've got the resonance stability of that leaving group, and then we decrease from there as we're going down. All right? So that helps to explain and helps us understand why the reactivity series is going the way that it is when we take a look at these carboxylic acid derivatives. So in the next set of lectures, we're going to start with the acid chloride, and we're going to look at how can I, number one, turn a carboxylic acid into an acid chloride, and then number two, once I have an acid chloride, what else can I make with it? Well, we know we could make anhydrides, esters, and amides. Turns out you can also turn it back into a carboxylic acid. And then there's several other reactions, including reductions with hydrides and Grignard reagents that we can use with that. Pretty much most nucleophilic reactions. So I will see you guys for the next lecture. Hopefully you found this helpful in understanding the acid derivative series for carboxylic acids. Please remember to like the video if it helped, and if you leave comments, I will try to get back to you as soon as possible. The other thing I would just ask is if you're constantly learning, please subscribe to the channel because it really helps us out in terms of support. Other than that, I hope you guys have a fantastic rest of the day, and thanks for studying with us. Take care.